Hello, everyone. Now that we have some idea what stoichiometry is and how to kind of go about these stoichiometric relationships, let's put them into practice. And so in this video, we're going to be focusing on sequence reactions and limiting reaction problems. And so sequence reaction, they're also called by a couple different names. You might hear them as cascade reactions as well. But basically, it's just a reaction that occurs and sets off another reaction, which sets off another reaction, and so on and so forth. The way that this happens is usually the product of the first reaction becomes a reactant in the next one and becomes a product, becomes a reactant, so on and so forth. And so if you have a couple different individual reactions, or sometimes they're called elementary steps, then you can actually put all these together to come up with an overall equation, or sometimes referred to as a net equation. And so the way that this works is you just, again, it's not as complicated as a lot of students try to make it. So just follow my simple few steps and hopefully it should clear up some confusion. And so the first thing is you should already have your equations given to you. Again, there's elementary steps or some type of equations. Make sure that they're actually balanced. And then from there, you need to figure out some commonality between those two. Meaning the fact one of those reactants and or products, one of those compounds is going to appear in both of those equations. You need to make sure that that one thing is balanced in those two equations. Say if you have two of the compounds in equation one and you have 16 in the other equation, those equations are not tied to one another because you have an imbalance between those two steps. What you need to do is make sure that your one commonality, your one common thread between all of your balanced equations is the same, because that's the only way you're going to be able to add these two to each other. And the last thing is to add the two equations to each other once you've kind of finagled with it and made everything right. But add them together, make sure everything cancels out that you don't want in the long run, and then you'll have a brand new balanced equation that is composed of your 2 or 3 or 16 individual equations. For example, whenever you are roasting, it's basically an extraction of copper from chocolate. And so in the step here, you're going to react copper oxide with powdered carbon to yield copper metal and carbon monoxide. And so I've given you the two-step process here with the individual equations, and I want you to write out a balanced overall equation. And so this balanced equations that I have here, which again, if I do not tell you that they're balanced, don't safely assume that they are. Just make sure that they are balanced before you start doing the additional steps. And so in these two equations, you can see that Cu2O appears in my top equation as a product, and Cu2O is a reactant in my second equation. And so when we kind of go through, and again, I'll get rid of all this BS and make these bigger for you here. And so if you see the Cu2O on the top is a solid and the Cu2O on the bottom is a solid, so they are the same compound. The problem exists in the fact that in the first step, I am creating two Cu2Os. In that second step, I am only using up one of them. And so because of that, this is not a balanced relationship between the two equations. In order to make things balanced, I can just throw a 2 in front of that Cu2O on the bottom there, but I can't just single it out. I need to make sure if I'm going to change that Cu2O on the bottom, we have to make sure that everything is changed with it as well. And so in this instance, I'm not just going to multiply this compound by 2, I need to multiply this entire equation by 2. And again, I know it seems kind of goofy, but you have to remember the only real important part of a balanced chemical equation is the ratio. And so here I'm telling you one of these copper oxides plus one carbon gives you 2 copper plus plus a carbon monoxide. It's the same exact thing as if I do this. And so now I'm saying 2 copper oxides plus 2 carbons gives you 4 coppers and 2 carbon monoxides. The ratio is still the same. But then now I have a balanced equation or balanced relationship between equation 1 and equation 2. Because I'm going to create 2 Cu2Os and I'm going to use up 2 Cu2Os. And so now that those two guys are balanced, that means everything else in these two equations have to be balanced as well. And so now if I want to write out an overall equation or a net equation, I just need to group all the reactants together and group all the products together in one single equation. Or take everything on the left side of the arrows, like 2 Cu2S plus the 3 O2s plus the 2 Cu2Os plus the 2 carbons, and then take everything on the product side, or the 2 Cu2Os plus the 2 SO2s plus 4 coppers plus 2 carbon monoxides. But once you write this out, then you should kind of start seeing that 2U or 2 Cu2S, no, wrong one, the 2 Cu2Os, they don't do anything. They begin and end up being the same thing. And so in your net equation, you're not really interested in the guys that stay the same. You're only interested in the things that actually changed. And so here you can actually mark out your 2Cu2OS and rewrite your balanced overall equation without them in there. And so please note, those are the only two guys that disappeared. Everything else is going to be exactly the same in the products and the reactant side. And so, why the heck would you do that? Let's answer another question with another practice. And so the decomposition of nitrogen dioxide into nitric oxide and oxygen is believed to happen in a two-step process. Now I want to know how many moles of O2 will be produced from 5 moles of NO2. 5.0 moles of NO2. And so right now the problem kind of comes about that I'm giving you information about moles of NO2, which is all great because it's sitting right there. But my question is, how many moles of O2? If you look at this first equation, moles of NO2 is not tied to O2. This is equation 1, this is equation 2. And so there is no direct conversion or relationship between our NO2 and our O2 at this point in time. But luckily for us, in both of these equations, NO3 exists. And so because both the NO3s exist in these two equations, then again, there is a way to connect them. Luckily for this particular problem, I didn't want to blow your minds more than I already have. And so they're already balanced. There's one NO3 being produced, and there's another mole of NO3 being chewed up at that same moment. And so here you can just simply mark those out and write an overall net equation of 2NO2 plus your 2 NOs gives you, or plus O2. And please note, the 2 NO2s, there's a 1 NO in equation 1 and 1 NO in equation 2. That's where they came from. And so now, with this new balanced overall equation, now we have a relationship between our NO2s and our O2s. And so from there, you can just use stoichiometry the way we did or visited in the previous video, and you can go 5 moles of NO2, which we were given, using the conversion of 1 mole of O2 per 2 moles of NO2 from our new balanced equation 1 and 2. And then we end up with 2.5 moles of O2. And so this is why balancing these equations out firsthand and then figuring out the overall equation is actually necessary before you can even start doing the stoichiometry. And so, as I kind of stated in the previous video, I know not all of you are fans of chemistry to the extent I am. So let's go back to breakfast for a minute. And so, I know being a poor college student, it's just going to happen in life. That's part of growing up. But I am a father of a child who seems to have a never-ending appetite, so I have the exact same feeling as you guys. So whenever I open up my pantry, I'm just trying to make the best out of whatever I have available. And so say, for instance, I still want my pancakes, and I still have the same recipe of 1 cup of flour to 2 eggs to half a teaspoon of baking powder will produce my 5 pancakes. But again, I want to make as many pancakes as possible. So when I open up my pantry and my refrigerator, I find 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. And so again, right off the top of my head, I'm trying to figure out how many pancakes I can make. But the problem kind of comes around is none of those guys are tied to one another. Cups of flour, eggs, and baking powder, those are all tied to one another. But at this point, that's way too many variables to kind of figure out all in one swoop. And so the easiest way you can kind of figure this out is look at each one of your ingredients individually. Figure out how many pancakes your 3 cups of flour would create. Figure out how many pancakes your 10 eggs could create. Figure out how many pancakes your 4 teaspoons of baking powder can create. And from there, you'll get a better idea or better sense of what you're trying to look for. So let's do that here. And so as I stated previously, using my balanced chemical ingredient list here, if we have 3 cups of flour, the relationship between flour and pancakes is 1 cup of flour will produce 5 pancakes. Or with the conversion, flour needs to go on the bottom, but you have 5 pancakes was produced from 1 cup of flour, so we have the potential of creating 15 pancakes from our flour. Doing the same thing with the eggs, we know we need 2 eggs to create 5 pancakes, and so 10 eggs can potentially create 25 pancakes. And then the last one we have here is the 4 teaspoons of baking powder. We know half a teaspoon of baking powder will produce 5 pancakes, so our 4 teaspoons of baking powder can produce 40 pancakes. And as awesome of a breakfast 40 pancake sounds, unfortunately, it's just make believe. Because in this situation, the minimum number that you can potentially create is going to be the maximum amount of pancakes you're going to be able to produce. So let me say that one more time, as confusing as it sounds. The minimum amount that is potentially created from your individual ingredients is only going to be the maximum amount of pancakes you can actually produce. And so here, our 15 pancakes is the least amount of potential products here. And again, fortunately, that's the maximum number that we're ever going to reach with these ingredients. Because after you use your 3 cups of flour, after you've created your 15 pancakes, you're all out of flour. Your flour is out. You're done with flour. And so if you, for some reason, continued mixing your stuff, you would now just be mixing eggs and baking powder, and you cannot pay me enough to try to eat that stuff. And so in this situation, we have come across our chemical reactions in some very special terms that we're going to be dealing with. And so for any type of chemical equation, whenever you have more than one reactant, it is most likely not going to be a perfect mixture between the two to give you a perfect combination. And what I mean by that is if you're working in a lab, you're not going to measure out exactly 1 gram of hydrogen, 1 gram of oxygen, and end up with exactly 2 grams of water. It doesn't work that way. If you mix 1 gram of hydrogen and 1 gram of oxygen, one of those guys is going to run out first. And so the reactant that runs out first is referred to as the limiting reactant. So the limiting reactant limits the amount of product that can be produced. Once you are completely out of one of your reactants, the reaction has to stop. If you don't have all the ingredients for your pancakes, you can't make pancakes. You can make eggs, that's fine, but you can't make pancakes without your flour and your baking powder and your eggs and everything else included there. And so once the limiting reactant is gone, everything stops. It comes to a complete halt because you can't do anything else. And so any of the reactants that are not consumed all the way, any of them that are not the limiting reactant, are referred to as the excess reactant. And so once you have determined the limiting reactant, the great thing about that is it's always going to be tied to what they call the theoretical yield. And so if I go back to my previous example here, my 3 cups of flour are going to be the thing that runs out first. So that 3 cups of flour is going to be the limiting reactant. Your 10 eggs and your 4 teaspoons of baking powder, you're going to have some left over, and so both of those are going to be in excess. But that 15 pancakes, that is the theoretical yield. That just means that theoretically, if you did everything 100% perfectly, you will end up with 15 pancakes. As I stated, the limiting reactant and the theoretical yield are tied to one another. If you know the limiting reactant, it's always going to result in the theoretical yield. The problem becomes figuring out which one your limiting reactant is first before you move on and do all that additional work. And so, if we look at our balanced equation of methane here, and so remember, if we have 1 molecule of CH4 and 2 molecules of O2 and 1 molecule of CO2 and 2 molecules of H2O, typically we don't talk about it in terms of molecules. And so, but again, in this situation, the problem I'm going to ask right here does, and so we'll just deal with it that way. And so, if we have this balanced chemical equation, and I want to figure out if I have 5 molecules of CH4 and 8 molecules of O2, which one is the limiting reactant? And so as I kind of covered in the previous slides, you want to just take this one step at a time. Convert each of your individual reactants into their CO or into a product, and then again, figure out which one is in the least amount of potential product. And so for this problem, it doesn't matter which product you choose. You can convert your CH4 and your O2 into CO2, or you can convert your CH4 and your O2 into H2O. The only main thing you have to pay attention to within those situations is to convert both of them into the same thing. And so don't convert CH4 into CO2 and then O2 into H2O, because you defeated the whole purpose of the calculation. And so I just chose CO2 just because it's first, and so it was a shorter arrow. And so first thing we're going to look at is convert our CH4s into our CO2s. Using the balanced chemical equation, if we have 5 molecules of CH4 and it's a 1-to-1 relationship between CH4 and CO2, we know that we better end up with 5 CO2s, potentially. Do the same thing with our O2s. Convert our O2s and CO2s, and according to the balanced chemical equation, the relationship is going to be 2 O2s for every 1 CO2s. And so if we have 8 O2s, we can potentially create 4 CO2s. And so in this case, you need to figure out which one of your potential products is going to be the least amount. And so we have 5 CO2s coming from the CH4, or 4 CO2s coming from the O2. So in this case, our 4 CO2s is going to be smaller than 5 CO2s, and so this is going to be our theoretical yield. Because this is our theoretical yield, then we know that our O2s is going to be the limiting reactant. Alright, so now that we know limiting reactants and excess reactants and theoretical yields, I can throw 2 more terms into this mix, and again, they're not too much more complicated, but whenever you're working in the lab, if you were to do this experiment 100% perfectly, at some point something's going to mess up. You're either going to spill a little bit whenever you're transferring it to the scale, or as you're walking by, some fellow classmate of yours is going to sneeze right on top of your compound and it's going to fly over the floor. At some point, all chemists mess up. And again, even sometimes it's not even them messing up, it's the actual experiment that has some issues. And so whenever you are working in a lab, whatever you actually end up with is what they call the actual yield. And so recall, the theoretical yield is what were to happen if you theoretically did everything 100% perfectly. But even the best chemists in the world, they still rarely ever get to the 100% theoretical yield, just because we're humans, we mess up. And so when we figure out the actual yield, you can only do this in the lab, or I have to give it to you. And so if you ever see the term or the chemical reactions produced this amount of product, or yielded this amount of product, that's usually when they're talking about the actual yield. But as I stated, theoretical yield, that can be calculated before you even step into the lab. Actual yield, you actually need to do the experiment to figure this stuff out. And so the percent yield is going to be the actual yield over theoretical yield. And again, I know this seems kind of like a goofy equation, but you've all messed with this equation in the past. Because when you look at your exam grade is calculated by the questions you actually got correct out of the questions you theoretically should have gotten correct. And so in this case, a percent, as I've stated in previous videos, a percent is nothing more than stuff out of the total amount of things you're looking at. And so if we want to talk about the mass of excess, and so ammonia can be synthesized from this chemical reaction. And so 2NO plus 5H2 gives you 2NH3 plus 2H2O. And so I'm telling you, a chemical vessel initially contains 4 grams of NO and 2 grams of H2 and produces 1.97 grams of NH3. And so just a side note, a reaction vessel, I just mean anything, like a container that is sealed so nothing else is getting into or out of it. And so the questions that I want you to answer is questions I am going to answer is how much of the excess reactant is left after the reaction has gone to completion, and what is the percent yield for this reaction. And just to if you're working a little bit ahead of me while I'm going through the video, here is the molar mass or molecular masses of your NO, your H2, and your NH3. Those be useful. They're also going to be on this next slide. So, to make everything a little bit more compact, I shoved everything up into the left corner here. And so we still have our balanced chemical equation. And we are given grams of NO and grams of H2. And so one thing I have to point out at this point is anytime you are given a word problem or any type of chemistry problem, and I give you information about more than one reactant, or if I don't specifically say NO is being mixed with excess H2O, you're always going to be looking at a limiting reactant problem. So if I give you information about two different things inside a word problem, you first have to figure out the limiting reactant problem, like part of that, before you can move any further into the problem. And so, for this particular case and the previous ones, I kind of talked about moles to moles. But here I'm giving you 4 grams of NO, and I'm also giving you 2 grams of H2, and I'm telling you once you mix these two things together, you're going to create 1.97 grams of NH3. And so, 1.97 grams of NH3 is going to be, I guess, an indicator of which one of the products you want to convert both of these into. And so, for instance, in this one, because we have NH3 as a product and H2O as a product, you can technically convert your NO into H2O and your H2 into H2O if you wanted to, but it'd be kind of a point, or I guess pointless, because I'm telling you information about NH3. So let's just use that one. And so the first step, convert your grams of NO into grams of NH3. And so here, this is why I gave you the molar mass of this stuff. We can't do anything with grams. Grams will not tell you diddly squat. And so you need to convert your grams of NO into moles of NO. And then from moles of NO, we have a balanced chemical equation that tells us the relationship between moles of NO and moles of NH3. Once we're in moles of NH3, I give you the molar mass, and so you need to go from moles of NH3 to mass of NH3. And then do exactly the same thing with your H2. You go from mass of H2 to moles of H2 to moles of NH3 to grams of NH3. And so here's all the math for that. And so as I kind of stated, these, I understand, it's a lot of math. It is a lot of stuff to write down to put into your calculator. But hopefully, after you do a few of these practice problems, it kind of becomes like you start getting into the flow of things. And so great thing for us is this problem or this scheme, it will never change. You're still always going to go from mass to moles to moles to mass, mass to moles to moles to mass, mass to moles to moles to mass. Or if you want to get fancy, volume to moles to mass. But moles to moles is always going to be the same thing here. And so first step is taken care of. We convert our grams of NO and grams of H2 into grams of something common that we can take a look at. And so comparing our 2.27 grams of NH3 to our 6.75 grams of NH3, again, we have our 2.27 being the least of those potential products, and so we know we are going to have our NO as our limiting reactant, our H2 is going to be the excess reactant, and our NH3 is going to be the theoretical yield. And so, the next part we have to kind of, I guess just throw this out here, that's never going to happen. And so the excess that like reactant reacted, whenever you kind of go through and look at this, it's going to kind of be the 6.75 is just going to be, that box appeared out of like order in my animations. But that 6.75 grams is never going to happen. It's just a make-believe number that you can scratch out after you're finished with it. And so, so act like that box doesn't appear yet. And so now that we have these 6.75 grams as make-believe, we know that 2.27 grams, our theoretical yield, is the maximum amount of NH3 that's ever going to be produced. And so, kind of a trick question here, but if I were to take this 2.27 grams of NH3 and convert it back into grams of NO, hopefully what should you get? And so the answer should be 4 grams of NO, because that's the math you did to get to the 2.27 grams of NH3. And so the problem with converting your theoretical yield back into your limiting reactant is it's pointless, because you know your limiting reactant is all gone. In addition to that, once your 2.27 grams of NH3 has been produced, how much of your NO should you have left over? And again, the answer should be none. It's the limiting reactant. It is why they call it the limiting reactant. It's all gone. But if that 2.27 grams of NH3 is created, how many grams of your H2 was going to be used up? And so this is where you can kind of figure out the amount of excess reactant that is going to be left over. And so if you take your theoretical yield and convert it back into the limiting reactant, that's a waste of your time. But if you take your theoretical yield and work it back into the excess reactant, you are going to be able to determine the excess reactant that actually reacted. And so converting the 2.27 grams of NH3 back into the H2, it's telling you that you use 0.67 grams of H2 to produce 2.27 grams of NH3. Or in the whole big scheme of things, 0.67 grams of H2 plus 2.27 grams of NH3. Nope, see, I messed that up. Sorry. 0.67 grams of H2 plus 4.0 grams of NO produced exactly 2.27 grams of NH3. So once you know the mass of the H2 that was used up, that was actually used in the reaction, you can subtract it from the mass of the H2 that you began with, and it tells you that there's 1.33 grams of our H2 left over inside of the reaction after everything has gone to completion. So please note, this excess reactant is in the exact same form it started off in. At this situation, as soon as the 4 grams of NO have reacted with 0.67 grams of the H2, the leftover H2 is just bouncing around like, oh, well, I guess we lost our shot. Nothing else is going to happen. And so they will just keep bouncing around as H2 for the rest of the eternity that they're inside that reaction vessel. And so there was a second half to the problem. So in this case, once you know your theoretical yield, and if I tell you the actual yield, or in this case, I tell you that I mixed 4 grams of NO plus 2 grams of H2, and I actually produced 1.97 grams of NH3. And so for this one, you just need to remember what the equation is. It's always going to be your actual over your theoretical, or what you actually ended up with over what you could have potentially ended up with, and you end up with 86.8% yield. And so one thing I have to kind of mention about percent yields, some of you, when we are working in the lab, if you work in the lab again, like hands-on, then some of you will be like way overly excited if you get something like a 103% yield. And unfortunately, that's pretty much as bad as having a 70% yield, because no matter what your high school teacher told you, you cannot have any more than 100%. 100% just doesn't exist. And so if you are in the lab and you have something like 103% yield, that just means that you have impurities or your stuff is soaking wet. There's something outside of the realm of natural science that is working on in that situation. All right, everyone, that's all I have for Chapter 3. So please make sure to read all the material in the book. Check out my other videos. I have a lot of other stuff on Blackboard for you to look over and do some practice. And if worse comes to worse, you can always email me.